All right, so this is example 2 from topic 9. We're going to start right where the other video left off here and get into this example, okay? So the goal here is to design this wooden beam with the supports shown here, and it's carrying a distributed load of 12 kilonewtons per meter, and we want to know what the smallest possible width we can have given a height to width ratio of 1.5 if our allowable bending stress and shear stress are given as follows, okay? One little thing we can do here is we can neglect the weight of the beam, so we don't have to do that extra calculation that we did in the previous example. We can kind of just leave out the weight of the beam here and assume that it's negligible for the section that we pick. Okay, so the first thing I'm going to do is I'm going to redraw this here with supports. This is the distributed load. Okay, whatever. All right, so that's the distributed load of 12 kilonewtons per meter. And then we have our two supports. One would be here, we'll call this AY, and one would be here, we'll call this BY, and this is 1 meter away, this is 3 meters away, and really that's all we have for our shear and moment. So to get AY and BY, I'm going to sum moments about point B, set them equal to 0, and let's just write in here, we have 12 times 4, so we have 48 kilonewtons for that resultant of the distributed load. Okay, so now I'm going to have an AY, this would be a negative AY times 3, and then I have a plus 48 times 2 away from BY, and that's going to be 0. And here I would get AY equals 32 kilonewtons. And then summing up forces in the Y direction, I would get 16 kilonewtons for BY. Okay, and now I can go about constructing my shear and moment diagrams. Okay, and here this is V in kilonewton, M in kilonewton meter. Okay, so let's start here. We start with a shear of 0. We have a constant distributed load pushing down. So after 1 meter, it's going to be 1 times 12, negative 12. Then I have 32 kilonewtons pushing up, which means I'm going to be pushed up here to a value of positive 20. And then I'm going to, by the end of this, I'm going to push down by another 12 times 3, which is 36. So 20 minus 36 would take me to negative 16. And then I get pushed back up by a positive 16, and everything closes, all looks good. Okay. Now here for moment, I'm going to use a shear diagram to guide me for the moment. So I start with a moment of 0 because I have no applied moment on the beam. And I know that here my area is 1/2 times 12 times 1, which is 6, which means I'm going to have to be at a value of negative 6 here. I start with a slope of 0 because the value of my shear is 0. I will end with a slope of negative 12, and all I have to do is connect that. Terrible connection. Let me try that again. Connect those two points like that. Okay. So for reference here, we know that our distributed load is constant, which means our V is linear, which means M is second order. Not sure what I just spelled there. Second order. Okay. There we go. And here, to figure out, I know that I'm going to have a local max here because I have a positive and then negative. So I know that my value, the value of this is going to look something like this, with this being my max moment. Okay. Oh, whoops. Did I go past the X value? Sorry, I have to close at 0. Let me try that again. Okay, now to find that M max, I'm gonna have to make a cut here because I don't know at what point this crosses the x-axis. Okay, so what I'm gonna do is I'm gonna make a cut. Okay, so I'm gonna make a cut here. I still have, and then I know that this happens after AY actually, so I wanna make my cut after AY. So let's say AY is right here. This is my 1 meter. I'll call this whole distance here X. And this is my cut, which means I've exposed some V, some M. And then of course, let's not forget that I still have this distributed load of 12 kilonewton per meter, which means I'll have in the middle of this section 12x. Alrighty, so now let's sum forces in the y direction. I get negative V plus 32 minus 12x equals 0, and I get V is equal to 32 minus 12x. If I want to figure out where it's hits the x-axis, set it equal to 0, and I get 32 equals 12x, and I get x equals 2.667. Okay, so that's where this here, or I can actually say that this, if I want to subtract the 1, is 1.667 meters. Okay, if that's 1.667, this here is 1.333 meters, and then just for completeness sake, this is my 1 meter. Okay, if that's 1.667, I have everything I need then, because 1.6667 times 20 times 0.5 here, so let me write this here. I want the area, so let me put this back in purple. 1/2 times 20 times 0.5 is equal to, oh wait, not 0.5, what am I doing? Times 1.667 is equal to 16.667, which means if I'm at -6, I need to go -6 plus 16.667, and I'm at here a value of 10.667. That's how I can get my max moment. Okay, so now I have my Vmax, which is that 20 kilonewton, and my Mmax, which is the 10.667 kilonewton meter. Okay, now I can move on. So everything we just did was statics. Now we can move on to the bending stress, okay? All right, so we know this nifty little formula we can use, S required equals M max over sigma allowable, and we can plug in M max. We're gonna put this in Newton meters because our sigma allowable here is also gonna go Newton per meter squared, and we get 0.00119 meters cubed, okay? And we'll call the width A. I think they put that here. So they drew this little, that's not even, but okay. They called this A, and they called this 1.5A. Okay, so we'll assume the width is A, and we'll call the height 1.5A. Then we know that our S required is also equal to the ratio of I over C, which means that we can say 0.00119 equals the moment of inertia of this, which is 1 over 12A times 1.5A cubed divided by 0.75A, and then we get a cubed is 0.003160, and we can solve for a as 0.147 meters. Okay, so this is the a value that we can solve for. Now we need to check the shear stress. Make sure everything is good with shear. So we're going to apply shear stress for the rectangular case. This is, you can see the previous topic on shear here. We also know that tau max for this rectangular section we can approximate using this formula, and this also works fine. So if you are wondering where I'm getting these formulas from, you need to go back to the topic on shear stress and see why we're using this 1.5 V max over A and what's happening here, okay? So I'm going to plug in maximum shear divided by 0.147, the A we just calculated, times 1.5 times 0.147, and I get 0.929 megapascals for shear, which is greater than our allowable, right? And this is a wood section, remember? So this fails in shear. So what do we need to do? We need to redesign. Okay, so now we're going to redesign based on shear. So our tau allowable, again, is 1.5 V max over A. So let's plug in. We have 600 kilonewtons per meter squared is equal to 1.5 times 20 times 10 cubed over the area. And we can solve for an A value of 0.183, which is less, makes sense. So we already know this is going to resist bending because we knew that an A of 0.147 would resist bending. So a bigger section, of course, will still work. Okay, so this here is our final answer. Okay, so let's do, I think this is our last one for this topic. Let's do one more. Okay, and I'm going to post a final review for you guys too, that will let you guys kind of see some more difficult problems and how to apply and solve for those. But really, this will cover these three problems. Will cover kind of everything you need to know about beam design, and then just apply it to maybe some more difficult problems. Okay, but this here is a little bit more challenging because what's happening is we have a couple of things that we need to look out for. So this is very similar to your quiz question. We have a T-shaped section made of two boards, and they're nailed together. And our allowable bending stress is given here, our allowable shear stress is given, and then we also need to make sure that, or we need to figure out what our max spacing of the nails is to hold the boards together if we know that each nail can resist 1.5 kilonewtons in shear. So your quiz problem still wasn't a design problem because I didn't ask you to tell me that, I just asked you to check it. This one is asking what the spacing is going to be. So this is why this is design. You are completely coming up with that on your own based on the requirements of the problem. Okay, so we're going to start with our shear and moment here, or solving reactions, all the static stuff that we need to do. We have a BY, we have a DY, and I'm going to start, let's do this here, some moments, let's do it about B. Counterclockwise is positive. dy times 4 minus 1.5 times 2 minus, and then the resultant here is just 1.5 times 2. So minus 1 times 1 equals 0. And we get dy equals, I think this is just 1, right? Because we have 4 dy equals 1 plus 1, 2, dy equals 2, a half. me see what happened. I have a 1 written down. Let me see what I did wrong here. dy minus 1.5 times 2. Yeah. Let's check my work. Let's do this again. Okay. We would have positive dy times 4 meters. Oh, minus 1.5. I think that was my problem, times 2, not 0.5. There we go. That was my problem. This is a 1.5 times 2. Okay, now minus 1 times 1 equals 0. Now my dy will be 1 kilonewton. There we go, because it's 3 over 2, 2 plus 1 here. This is going to be 3 over 2 times 2, so we have a 3. Negative 3 minus 1, we have a 4. When you divide by 4, you get a 1. Okay, all good, sorry. All right, so if dy is 1, then our by has to be 1.5, because those have to equal 2, the 1.5 plus 0.5. And we can now draw our shear and moment diagrams. Okay. Alrighty, so we're going to start here at positive 1.5 on our shear diagram. And by the time we get to the end here, we'll need to go down by 1. The whole value of the distributed load, which will put us at a 0.5. So here will be at 0.5. How did I get that? I'll show you. We know that the total value of the distributed load is 1. So if we're at 1.5, by the time the distributed load finishes, which is here, we need to subtract 1, and we're left with 0.5. That's why this is 0.5. Okay. At this point, we also get pushed down by 1.5. So 0.5 minus 1.5 would bring us here to negative 1. No change until we get to D, and then we get pushed back up by 1. Everything closes, so we know we did this correctly. Okay, now for a moment, we start at 0 moment. Okay, the value here of the area, I'm going to call, actually, let's just do this. I'll call this area 1, I'll call this area 2. Okay, area 1, we have 0.5 times 2 meters plus 1, which is the leftover of that triangle, or I should start with a half, plus 1/2 times 1 times 2, and this here is going to take me to 2. So I know the value here needs to be at 2, and I'm going to have a positive 1.5 slope, and I'm going to have a little bit less of a slope here, so I'm just going to connect that like that. And then here, I know that I have to go down with a straight line because I have a constant value for that portion. Okay, and this max value here is 2. Okay, so from that, we can get our Vmax, which is 1.5. And we can get our Mmax, which is 2. And now we can start with the bending stress portion. Okay, so first thing we want to do, because this is a T shape here, I'll probably just copy this. We have a T-shaped cross-section, so what we want to do here, carefully calculate our Y bar. So we have the 0.1 times 0.03 times 0.2 plus 0.215 times 0.03 times 0.2 divided by just the area, so the 0.03 times 0.2 plus 0.03 times 0.2, and we get 0.1575 meters. And then we can calculate our moment of inertia. I'm going to do parallel axis theorem. So we have the 1 over 12 times 0.03, this is for the flange, times the 0.2 cubed, plus now the AD squared, so the area of that section, times 0.2 times the distance away from the center to the neutral axis squared, and then plus the second portion, 1 over 12 times that 0.2 times 0.03 cubed, plus the area So you should be trying this and seeing if you can get this right value. And this should be a check because this is from some topics way back before this. So this should be, both of these should be very simple to get for you guys now. So make sure you're trying to get this and then you're just checking with this work. Okay, so our C value here, our C value is the 0.1575 meters. We require that our sigma allowable be greater than or equal to our M max C over I, right? We need to make sure that that's what's happening. We're given our sigma allowable as 12 times 10 to the 6 pascals, which needs to be greater than our maximum moment of 2 times 10 to the 3. Our C value, 1575, divided by 60.125 times 10 to the negative 6. And we get 5.24 times 10 to the 6 pascals, which is all good because it is less, this value is less than this value, so it checks out. So we are good when it comes to bending stress. Next check is shear stress. Okay, so the max shear stress in our beam here, if we remember, it's dependent on our Q value and our T value. But we know, if you remember from our shear stress profile, where does our max tau occur? So if this is our shear stress profile, we have little, bigger, biggest, smaller, smaller. This is a parabolic shape. So we know that the max here occurs at the neutral axis, right? And where is the neutral axis for this? Well, we know the neutral axis here occurs in the web. This is very important, right? That point, our T value is 0.03 meters. This is the smallest value in the cross section, right? So what we're going to do for simplicity, we can either use Q above or below. So rather than doing this in a two-part way, what we're going to do is we're going to use the Q value below. So let me draw this out here. Okay, so my neutral axis is here, let's say. And we know that this distance here is 0.1575 meters. Oh, and where was my, oh yes, sorry, okay. Here it is. Where this distance here is 0.0725. And I'm going to do my Q calculated from this bottom portion. So I'm going to say Q is equal to Y bar A prime. And I can say that's equal to 0.1575 over 2, the distance from the middle of that to the bottom right there, times 0.1575 times 0.03, the area of that. And that's just equal to 0.372 times 10 to the negative 3 meters cubed. Now I need to come here and check that my tau allowable, my allowable shear stress, is greater than or equal to V max Q over IT. Okay, so we have this 800 times 10 cubed pascals needs to be greater than or equal to 1.5 times 10 cubed times 0.372 times 10 to the negative 3 meters cubed divided by our moment of inertia, which we calculated earlier, and we get 309 times 10 cubed pascals, which is less than the 800, so we're good, we're okay. So we are fine in bending, we're fine in shear. We need to check the nail spacing now. Okay, so from our shear diagram, we see that our shear basically varies over this entire span. It's changing, right? Our nail spacing depends on the magnitude of the shear in the beam, and for simplicity and to be conservative, we can design the spacing on the basis of V equals 1.5. So we'll choose this V equals 1.5 kilonewtons for BC. So let me show you. So we'll design it based on the 1.5. We're not going to design it based on these different values. And then we'll design it based on the 1 for CD. And this is going to save us and make us be a little bit more efficient, save us some nails. Okay, so what we're doing here our nails here are joining the web and the flange like this, right? So our Q value here, we're going to take this 0.0725, which is the distance from the neutral axis up now, okay, we're going to subtract it from half of the thickness of that beam, or the web, and then we need to multiply by the area, so the 0.2 times 0.3, and we get 0.345 times 10 to the negative 3 meters cubed. And that's for this is for the nail spacing here. Okay. We're going to consider the shear flow. So we're going to do shear flow for BC. We're putting in the 1.5. Our moment of inertia. And then we're going to do it for QCD and use the BCD Q over I. And we end up getting 1 times 10 to the 3 here for the shear. And divided by, again, moment of inertia. And we get 5.74 kilonewtons per meter. And we know that one nail can resist 1.5 kilonewtons of shear. So our max spacing here is going to be our 1.5 kilonewton that it can resist, divided by the 8.61 kilonewtons per meter, and I get 0.174 meters. And then for SCD, I know that it's also 1.5 divided by 5.74, and I get 0.261 meters. And I'm going to put this into millimeters, but what I'm going to do is I'm going to round down to the nearest whole number, and usually we'll be a little bit conservative. And this is, again, there are multiple right answers here, so I'm going to use 150 millimeters and 250 millimeters for ease of construction. Okay, so as long as it's lower, you could have said 170, you could have said 160, but 150 and 250 are easily calculatable. Okay, so design problems, you can have different numbers. You could have also had different values of shear. You could have said, well, I'm going to leave it all with a max of 1.5 and be extra conservative, and then not round down as much when I get to these points. Okay, and those are all acceptable. So really, when you're doing these problems, you're going to have a different answer than the person next to you or the person next to them, and that's okay as long as you can justify why you were doing what you were doing. Okay, so that's really it for beam design. We'll go over a couple more problems in the final review for this, and you should be good.